Let's talk about the harmonic perturbation today. In my previous video, I discussed the Gaussian perturbation for time-dependent perturbation theory, and for the Gaussian perturbation, it illustrated the importance of the frequency components that matched the Bohr frequency of transition. Well, the frequency components that are far from the Bohr frequency of a particular transition, then they do not give rise to an appreciable probability for that transition to occur, right? And so now, because of such a reason, then one of the most efficient way to make a transition possible is then to impose a sinusoidal perturbation at the transition frequency, right? And so then this kind of, or this type of interaction will then be a resonant interaction, right? So now at some t is equal to 0, at some t is equal to 0, the time dependent perturbation Hamiltonian is turned on, right? And suppose that now this Hamiltonian can be separated into two different parts, particularly space and time parts, right? And so the Hamiltonian that is turned on is written in the following manner, that h prime of t, or h1 of t, is equal to 2 times v, and v is now a function of r, that is my space part, and then I have the time part, that is my cosine function cos of omega t, right? So this is the kind of perturbation, the sinusoidal perturbation, right? Okay, and well, we can then obviously write cosine in terms of exponentials, and so then we can write our Hamiltonian now in terms of exponentials. So doing so, it will become 2v as a function of r, that's r, not n, it looks like n, okay, r. And what is my cosine function in terms of exponentials? Well, it's exponential of my iota omega t and times the exponential of my negative iota omega t, right? And so this over here is my space part, and this thing over here is my time part, right? Now again, recall that I have previously discussed in my video on the transition probability that my expansion coefficients are written in the following manner, that my Cf as a function of time is equal to 1 over iota h bar, and the time integral from some 0 to t is then written as the matrix element f h1 as a function of t, I'm sorry, not iota, but I, some initial state, right? And exponential iota over h bar EF, the difference in energies of the states, minus EI times T prime, and close this, carried out over dt prime. Alright, well, let me mention something else over here as well, that you can read this thing over here as you have an initial state I, and then the Hamiltonian acts on it and takes it then to the final state F, right? Okay, So now that's out of the way. Our next step is then going to be to substitute this h1 as a function of time in our expansion for the expansion coefficients, right? In our expression, right, over here. So, well, what is h1 of t? It's over here. Now all I'll do is I'll put it in this equation over here. So I'll go to next page for that, and let's do it over here. So what I'll have is my CF as a function of t now can be written as 1 over iota h bar times time integral dt prime, right? And what will be inside our integral? Well, f h1 as a function of time, I, this is t, right? And the value of this h1 is from here, this thing, right? And so let me just instead put this value. So let me get rid of this. Okay, and what is it? Or the value of h1 as a function of time is, then I have my space part v of r. I'm not going to write the vector symbol on r anymore, so I hope it's understood that it's a vector position. And I have my exponential, so I'll have exponential I omega t times my exponential negative iota omega t, and this is the Hamiltonian, right? And then we have, for the expansion coefficient, the exponential of it over h bar ef minus ei, and let's close this exponential, right? And all of this is carried out over this dt prime. Okay, you can also imagine or take this iota times t as some imaginary time, and then there arises a concept of a Wick rotation, but well, that's not for our case over here. That's beyond our scope. So let's just go and simplify this expression that we have written a bit more, and then that will be equal to f. I can take outside the exponentials, right, from my Hamiltonian, but I'll obviously still be left with v inside because it's a function of position coordinate, and then that is an operator in quantum mechanics. So I cannot take v outside, right? So it will have to act on my initial state I, and then I'll have iota h bar time integral from some 0 to t. And what I'll do here is I'll combine these exponentials. So when I do that, what will I get, right? So first, also remember, I'll write it down here, then I'll erase it, that my omega fi was what? It was simply ef minus ei over h bar, right? So this was my bar's frequency, right? So I'm going to substitute that for ef minus ei over h bar. I'm going to substitute omega fi, and and then I'm going to combine my exponentials together, right? So now let me just get rid of this thing quickly. Let's just increase the size. Okay, so now I'm going to combine these exponentials in terms of omega fi, right? And so I'll get iota. Now omega fi, for the one of the expressions I'll have minus omega right? And times t then, or let's say t prime, right? Because we're integrating from 0 to t, so let t prime be our dummy variable. And this exponential, and then we'll have another exponential, and that will be iota omega fi, this time with a positive sign, omega and t prime, right? And now let's close this exponential, and then all of this that we have over here, that will be carried out, the integral will be carried out with dt prime, right? Okay, so well, now next step is to take the integral, and after we take the integral, we carried out the integral, we are left with this thing here. Now upon the evaluation of the integral, you get exponential iota omega fi plus omega times t, right? And then minus 1 over here, right? And underneath you have iota omega fi plus omega, right? And this is your first, your first term over here, and then you have for the next exponential iota omega fi minus omega times t minus 1, right? Okay, like this. So minus 1 is outside the exponential, and all of this over iota omega fi minus omega, right? Okay, so then you have this brackets over here. Alright, so all I have done over here is taken the time integral, right? And then I am left with this quantity over here. Well, what we can do from here is we can write it in terms of a sine function, right? So let's go ahead and do that, right? So let me write that whole thing now as being equal to, or I'll need more space for this. So f v I over iota h bar, right? Okay, now we'll have my exponential iota omega fi plus omega times t all over this, all over 2, right? And let's close this exponential, and then you'll have your sine, right? Sine omega fi plus omega over 2 times t over, over omega fi plus omega over 2, right? And then you'll have another term over here, and I'll write it down over here. That will be plus exponential iota omega fi minus omega times t over 2, and you'll have another sine function that will be sine omega fi minus omega over 2 times t over omega fi minus omega over 2. Well, this is a pretty lengthy expression, but this will be very important for us. So we are also going to box this expression over here, and let me go ahead and just call this expression my equation. Let me call it star, right? So let's say that this is my equation star. Okay, so let's move on, and also let me tell you that this expression over here is my CF of t, right? Okay, so we are concerned with the probability, right? And so recall that my probability from my previous lecture I derived was given as going from some initial state to a final state is then the modulus square of my expansion coefficient as a function of time, right? So this thing over here, right? Well, now to find this probability, we will square the amplitude. We call these coefficients that I'm talking about, they are the amplitude, right? So we are going to modulus square these amplitude, and which will lead to some cross terms, right? We are talking about this expression over here. This is what we are calling the amplitude, right? And so it will lead to some cross terms and a very complicated expression, obviously, right? And this is what we will have to do if the two terms of the CF of t, right, inside these two terms. Wait, I'll just write it over here, right? These two terms, right, the terms that are inside these curly brackets over here, right? Okay, so well, if these two terms are of a comparable size, right, so, and that will be true in the case of if the frequency is far from a resonance frequency, right? So it's not close to a resonance frequency. Well, however, if that resonance condition is even almost satisfied, right, then one of the two terms inside these curly brackets is going to dominate the other one, right? And this is due to the fact that the denominator will approach to 0, right? And so to decide which term dominates, well, that is going to then depend on the difference of energies of the two states, right? And so let me write that down over here. So it's going to depend on this thing, EF minus EI, which is going to be equal to h cut omega fi, right? And well, this thing can either be let me just do this. So it can be either be positive, right, or it could be negative, right? So well, let's look at these two cases over here, right? And so first let's talk about case 1, let's call it. And so in case 1, we are going to say that say if the energy of my state I, right, so if this energy EI is less than the energy of my state F, well, then the energy difference, this thing over here, is going to be positive, right? So greater than 0. And the second term in my, let's go back here, in my equation star, right, this term over here, the second term is then going to be large for an excitation frequency that shall match the Bohr's frequency, right? So what that is the excitation frequency that I said is my omega and equal to omega fi, right? So in this particular case, the dominant probability amplitude is going to be for the transition happening from a lower state to a higher state, right? And we may call this thing over here, let's call it absorption, right? And so what's going to happen is, if this is the case, then let's say that these are my two energy states, right? So this is my state I and this is my state F. What's going to happen is a transition is going to happen from my lower state, from my lower state to my higher state F, right? So this is going to happen in the case of this thing over here, when my energy of my state I is less than state F, right? And so this is what we are going to say, that this thing is an absorption, right? And then, well, we're going to have another case. Let's call that case 2. Okay, right? And in this, if my energy of state I, so EI, is greater than my energy of state F, right? So then the energy difference, that is, let me write it over here again, that is my EF minus EI is going to be, that is equal to H bar omega Fi. Well, in this particular scenario, right, where EI is greater than EF, then the difference is going to be negative, right? And so the first term in my equation star, that is over here, this term over here, right, is then going to be large for an excitation frequency that matches the Bohr's frequency, right? And so if for this particular case, then that will be written as my excitation frequency is negative of my Bohr's frequency, right? This thing over here. Okay, so well, in this case, the dominant probability amplitude is going to be for the transition that is going to happen from an upper state to a lower state, right? So we could think of this as like a photon is being released and your electron falls from a higher state to a lower state, right? And so we are going to call this the emission, or in this example that I just gave, say emission of a photon, right, and causing the electron to fall from a higher state to a lower state. And the system basically emits energy to the external perturbation, right? Okay, so now because the emission is caused by an applied field that we talked about, the Hamiltonian, right? And so it is convenient to refer to this emission as stimulated emission, right? Okay. So now what we are going to see is that only one of these two terms in this thing over here, these are my two terms over here, one is this and the other one is this. So only one of these two terms is going to be important, or it's going to play a role in any particular experiment, right? And so we do not need to worry about both of them being together, right? So we can just omit one of them, right? And so, well, for now, let's come here, okay? And let's just consider, or let's just talk about the absorption case only, right? And because for the emission case, only the thing we would need to do is to change the sign of the preceding omega, right? The sign that is with my omega, right? So if it's positive, change it to negative. If it's negative, change it to positive, and you can go from absorption to emission, right? Okay, so then the probability of measuring my system in a final state, that is going to be, because we are talking about absorption only, then I can write this probability as my VFI. Now, actually I should have mentioned this before writing VFI. What is my VFI? VFI is just this matrix element over here, right? instead of writing Hamiltonian, let me just write it V, and I have I, right? I had this term in my expansion coefficient, right? So to just shorten it out, I'm writing it as VFI, right? So VFI squared, let's get back to the probability, VFI squared over H bar squared, all we're doing here is taking the square of my C f of t that we labeled as equation star, and we are ignoring one of the term, right? So the term for that is going to account for emission, we are going to ignore that and talk about absorption only. So I'll have my sine squared omega fi minus omega, right, over 2 times t, right, all this thing over my omega fi minus omega over 2 whole squared. Right. Okay. So now we can look at this expression of probability, right, in two different ways or two different point of views, right? So, well, one of these point of view is view it as a function of time, right? And when we do that, if we look at it as a function of time, you can see that there will be an oscillatory dependence, right? And that oscillatory dependence, right, let me write it over here. If we view it as a function of time, right, so the oscillatory dependence is going to be with a period of 2 pi over omega fi minus omega, and we're going to look at the graph, the probability distribution graph for this, right? Let me just draw it over. I'll draw it very roughly over here. So this is going to be my probability as a function of time, because we're looking at it as a function of time, and I'll have my time on my, say, x-axis, right? Okay, so this thing is going to look like an oscillatory dependence, and so this curve is going to be like this, right? It's actually going to touch 0, so let me just try doing that again, right? And so it's going to continue forever, right? And this difference between these 2 points over here, right, this difference is, I'll write it over here, is going to be of 2 pi times my omega fi minus omega, right? Okay, so this is how the probability is going to be oscillatory, right? If we view this thing as a function of time, if we view this probability over here as a function of time, right? And well, there is another point of view that we could take, and that is to look at that probability as a function of frequency. So as a function of frequency. And because the relation between frequency and time is just an inverse relation, right? And so when we do that, when we look at it as a function of frequency, then the transition probability is going to display the expected resonance behavior, right? And it's going to be with a peak in probabilities at my omega equals omega fi, right? Okay, so, well, let me just draw again roughly the graph. What will that look like for this thing? So it's going to be, let me do it. We'll have here my probability, right, as a function of my frequency now, and over here I'll have my frequency, and it's going to gradually start increasing like this, and then it will peak at one point, and then it will come back down, and then it will go back to 0, right? So it's going to display a resonance behavior, right? and the peak is at my this thing over here where my omega is equal to omega Fi, right? Okay, and well, the difference is going to be this difference over here is then equal to, right, I'll do it over here, is equal to my 4 pi over t. So this is the graph that we get when we look at it, look at the probability as a function of frequency. And so the resonance curve has a finite width, right? And what that implies is that my resonance condition, that is omega equals omega Fi over here, is not an exact requirement, right? Rather, it is a spread of my frequencies that are my delta omega that causes this appreciable transition probability. And so the frequency width of the probability is going to be approximately equal to, let me write it down over here, the frequency width is approximately equal to delta omega, that is 4 pi over t, right? And the t over here is the duration of my interaction, right? So then we can go ahead and let me go to the next page and write this thing as my delta t times delta omega is approximately equal to 4 pi over delta t, right? That's my delta omega, and then we have times delta t, and so we get rid of this thing and we are left with 4 pi, right? Okay, so if you look at this, what is this thing? This thing over here is actually the Fourier frequency time uncertainty relation, right? And so what we could do over here is we could use this relation over here that my delta E is simply equal to my h bar delta omega, right? And so we can replace for delta omega in this above expression or equation over here, and we can get a relation of my delta t times delta E, right? So delta E times delta t is then going to be approximately equal to my h bar, right, delta omega times delta t. But we have just seen over here, right, that my delta t times delta omega is simply 4 pi, and so we can write this thing as h bar times 4 pi, and we can reject or neglect 4 pi because when we do that it is still consistent with our approximation, right? And so we can say that this thing is then approximately equal to my h bar. So we have found this relation between delta E and delta T, that delta E times delta E is approximately equal to h bar, right? And what this result means is that the longer you're going to observe your system, the better you can measure its energy, right? So that's what this relation tells you, right? Okay, and again, this relation is actually the, it's called the Fourier frequency time uncertainty relation, and from there we went on to find the find this relation between E, energy, and time, right? All right, so moving on, note that for the frequency representation, which we did over here, the resonance curve resembles the Dirac delta function, right? So the Dirac delta function is almost it's zero everywhere except for at one point it peaks and then it goes back to zero, right? So it's like a pulse kind of function. And so in that limit, the frequency with delta omega, that is this thing over here, for pi over t is going to go to 0, or it's going to approach 0, which simply implies that for this thing to go to 0, then my t has to go to infinity. So my t will go to infinity, and then this 4 pi over t will go to 0. So well, let's move or go back here to a new page, and well, under this certain limit, then the sinc function that we had in our probability, right, which was let me write it down over here, sine squared omega fi minus omega over 2 times t over omega fi minus omega over 2 squared, right? This is the sinc function, and well, in this limit where t goes to infinity, or my delta omega goes to 0, this sinc function is then going to become a delta function, right? And so what we can do is we can say that when we take the limit of this function with t approaching to infinity, or for a very large t, this thing over here then is equal to 2 pi t times the delta function of my omega fi minus omega. Right, and with this then condition, we can simplify our probability of transition as being equal to 2 pi t over h bar squared times v mod square, or this was vfi, right, times my delta function, that is omega fi minus omega, right? So this is the probability. And where did I get this from? Well, first I used this relation over here, that under a limit where t approaches to infinity, the sinc function actually becomes a Dirac delta function. And let's go back over here. This is where I had this probability, right? So I have just replaced this whole sinc function with the Dirac delta function, and everything else remained the same, right? Okay, so let's just get rid of these arrows and go back over here. Right, so this basically this expression over here, this tells us that the probability is going to increase linearly with time, right? You can look at this expression and you can directly see that, right? It's obvious. So well, we have been focusing on this behavior as it is extremely common, right, compared to the oscillating probability, right? So the oscillating probability came from the fact when we were looking at the probability function as a function of time, but we have been rather focusing on the looking at it as a function of frequency, because it is much more common, right, compared to that oscillating probability. And well, the linear time dependence, as we said, is going to allow us to define the transition rate. And let's go to a new page. The transition rate is then going to be as the probability per unit time, right? So the probability of my transition per unit time. So we can write that as my transition rate as R from I to F. So this is the transition rate. That is simply going to be the time derivative of my probability function, right? The transition probability as a function of time. This is time over here, right? Okay. So with this over here, all we have to do is take the time derivative of this equation over here, right? This equation, let's call it equation lambda, right? And so let me go back here and look at this expression over here. Now what we have to do is we have to take the time derivative of this equation, lambda that I just said, right? So let's go ahead and do that. So when we do that, when we take this time derivative, what do we get is we get my transition rate from I to F is then going to be equal to 2 pi over h bar squared times VFI, right? VFI squared times my Dirac delta function, that is omega Fi minus omega. Okay, so this relation that we just derived over here is known as the transition rate, right? And this Dirac delta function has a very important significance in this expression over here, and that is that the Dirac delta function is here known as the energy conservation or conserving delta function, right? So it's the energy conserving delta function, and it requires that the quantum of energy causing this transition, right? Let's say that it's a photon, okay? So that should match the energy difference between the two states, right? Okay, now let's think of an example. So let's say that you have a solid, right? So in a solid, the band structure of the electronic energy levels represents a continuous range of allowed states, right? So there is a continuous range of these states that are allowed. So it's not discrete. That's my point, right? It's continuous. So in such cases, the relevant transition rate is then the sum over the rates to all of the accessible states, right? So, or moreover, we can assume that these rates are incoherent. And we do that so we can add all of these rates. And the rates here I'm talking about the probabilities, right? Rather than the amplitude. Okay? So let's do something for this example that we just have. Let's suppose that there is some G as a function of E, where this thing is known as the density of states per unit energy, such that this G of E times dE is then the number of energy levels. So it is the number of energy levels that are going to lie in between E and E plus some dE, right? So that's if you look at it in a form of circle, let's say that in this this is my E, right? And then you have some E plus some dE, right? So the difference between these two is of some dE, and this thing over here is then E plus dE, right? Okay, so well, with this then the total rate is then given as the integral over all of the rates, right? And so let's go ahead and write that integral down, okay? So when I do that, that is then my R I to F, the transition rate, is then equal to the integral. What are the limits going to be, right? So again, note that this is the total rate is given as the integral over all of these rates. So the limits are then, because we'll have now our final state, right? We have made this transition from initial to final state. So it's like, for example, this is your final state, EF. So you're going to integrate it where it's some of it is in here and some of it is in here. So you're going to look at above and below its boundary, right? So a little bit above and a little bit below. So let's get rid of this thing over here. And so then let's write our integral limits. Then this will be EF plus some E epsilon actually, right? And then let's write down here our transition that we just derived. That is h bar squared VFI modulus squared times the Dirac delta function omega Fi minus omega times my G as a function of energy. This is my density of the states, right? Times my dE. Alright, so, well, what is the next step? Well, we can write dE as h bar times d omega. So let's go ahead and do that. And so then this thing over here will then be equal to 2 pi over h bar squared VFI squared, right? We can take all of this outside the integral, and then we can have for our integral Dirac delta function omega Fi, right, minus omega G E, that is the density of the states, times my h bar d omega, right? And the limits are going to be same, EF minus EI, EF minus E actually, and EF plus this epsilon, right? Okay, so from here, note that the range of this integration, the limits I'm talking about, is not going to be important because of the fact that in here we have this Dirac delta function, right? And so the result of all of this expression is then going to be my R I to F. This transition rate is going to be equal to 2 pi over h bar, right? We'll not have square over here because it cancels out with the multiplicative h bar that we had, and this thing over here times the density of my states, right? Okay, so this expression over here is actually extremely important because this result is referred to as the Fermi's golden rule, right? And it is applied to, because it is very general, right? So it can be applied to many interaction types, right? So it is applicable for a lot of cases or a lot of interaction cases, right? And this expression over here is actually much more practical than the expression that I had, over here, right? This expression, because of the fact that this expression has the Dirac delta function and this one does not. And the Dirac delta function is actually pretty non-physical, right? And so in this expression it's gone, and therefore it's a lot more practical, right? And so, well, it has a lot, this Fermi's golden rule has actually a lot of applications, right? And one of these particular application is the electric dipole interaction. So, and it is actually one of the most important applications of the time-dependent perturbation theory, right? And this interaction is between an atom and an electromagnetic field, right? And so we can use then this Fermi's golden rule to understand the electric dipole interaction as well, right? And so for this particular video, this is going to be it, right? We have already done a lot of things in this video, right? And so perhaps in the next video we'll talk about the use of this Fermi's golden rule in understanding the electric dipole interaction, right? So that's it for this video.